morning, everyone. This is Sachin Fiske from Electrical Engineering Department, SND College of Engineering and Research Center. In the previous lecture, we discussed about the time domain analysis. In that, the transient analysis of first order system and second order system. The first order system is over. Today we are starting the second order system. So what the second order system contributes, let us see. Basically, this second order system exhibits a wide range of the responses which must be analyzed and described. Whereas in case of the first order system, varying a single parameter changes the speed of response, change in the parameters of a second order system can changes the form of the response. For example, a second order system can display characteristics much like a first order system or depending on the component value, display damp or pure oscillation for its transient response. See this, a general second order system is characterized by the following transfer function as G of S is equals to B upon S square plus AS plus B. Now we are going to rewrite the same transfer function in another way, that is G of S is equals to omega n square upon S square plus 2 sigma omega n of S plus omega n square. Means here B can be written as omega n square or A can be written as 2 sigma omega n, and again B can be written as omega n square in denominator. The function of S is considered as it is because we are going to convert from time domain to Laplace domain analysis. In case of the second order system, the undamped natural frequency of the second order system, which is a frequency of the oscillation of the system without damping, can be written as omega n in bracket omega n is equals to under root of B. Now for sigma, we can write sigma is equals to A upon 2 root of B, and it can be referred as the damping ratio of the second order system, which is a measure of a degree of resistance to change in its system output. Now here this pole omega n sigma plus omega n under root of sigma square minus 1 and omega n sigma minus omega n under root of sigma square minus 1 are the poles of the complex if value of sigma is less than 1. According to the value of sigma, a second order system can be set into one of the 4 categories. So different categories are underdamped system, overdamped system, undamped system, and critically damped system. In case of the underdamped system, when the system has 2 complex conjugate poles, means the value of sigma can be lies in between 0 to 1. In case of the overdamped system, when the system has 2 real distinct poles and it has the value, means sigma is greater than 1. In case of the undamped system, when the system has 2 imaginary poles, that is the value of the sigma is equals to 0. And in case of the critically damped system, when the system has 2 real but equal poles, that is sigma is equals to 1. Now we are moving towards the contrast of the physical reality. All these transient changes, which are also called as the transient response, but can be vanished after their disappearance. A new steady state operation is established, and in this respect, we may say that the transient describes the circuit behavior between 2 steady states, and old one which has the prior to change, and a new one which arises after changes. A few methods of the transient analysis are known: a classical method and the Cauchy's Heaviside method, that is called as CH operational method. The Fourier transformation method and the Laplace transformation method for the CH operation of the symbol method is based on replacing a derivative by a simple symbol. Although these operations are also used in the Laplace transform method. See this, the operation used in the Laplace method, that is CH operational method, is not a systematic and a rigorous as the Laplace transformation method. This chapter basically concerned with the classical method of the transient analysis, and this method is based on the determination of differential equation and splitting the solution into two components. One is natural and second one is force response. The classical method is fairly complicated, but mathematically it is a simple in engineering practices. Thus, in our present study, we will apply some known method of the steady state analysis, which will allow us to simplify the classical approach to the transient system. Let us therefore begin the study of the transient analysis by considering the simple series RC circuit. After switching, we get we will get a source. Basically, switching means switching operation can be done by in between R and C circuit and free circuit in which the capacitor C will discharge via the resistance R. Basically, to find the capacitor voltage, we shall write a differential equation which is accordance with the Kirchhoff voltage law, and it becomes RC into dVc upon dt plus Vc is equals to 0. A direct method of solving the equation is to write the equation in such a way that the variables are separated on both sides of the equation, and then to integrate on each side and multiplied by dt and dividing by Vc, as Vc is the capacitor voltage and we are going to find the capacitor voltage on each side, and hence we have to divide it by Vc, means we may arrange the variable to be separated. So ddt of Vc is equals to 1 upon Rc into dt. The solution may be obtained by integrating each side of the equation and by adding a constant of the equation, and the integration will deals with the ln, means log of Vc is equals to minus 1 upon Rc of t plus log of d. So the capacitor voltage will be identified at d into e to the power 1 upon Rc, and hence the constant d can be evaluated by substituting it into the original differential equation, and hence by identifying the value of t is equals to below 0, that is the final value theorem. Thank you.